Okay, so we can start. So welcome everybody for this MIG online seminar session. So it's my great pleasure today to introduce موفق بن شهرة. Well, Professor موفق, he is a full professor and research director at جلال اليابس University, Sidi Bel Abbas. He started his studies at I think جلال اليابس also, and
Yes.
he completed his magister at Tlemcen University. Then he moved back to Jilal Ilyabis University, where he got his PhD under the supervision of Abdelkader Bouchrif. Well, regarding the math, he was working mainly on differential equation and inclusion, of course, of different type, with application to evolution problem and control theory and so on. And I guess just to finish with the math, he was awarded the Muri Sudan Prize in 2008. So, and today his talk about the Banach Contraction principle, generalization, and application will be a good introduction to the techniques used in his papers. So, please, Professor Muwafaq.
Thank you for the presentation. First, I would like to thank the organizers for this invitation and for giving me the opportunity to present this conference. This conference is concerned with the Banach contraction principle and its generalization and applications. In my opinion, the Banach contraction principle is among the most used tool for the study of ordinary differential equations, partial differential equations, integral equations, and so on. In this conference, I will not present the fixed point theory. This is impossible to present it in one conference. Indeed, this theory is so developed and currently is considered as an ocean. So the main goal of my presentation is to introduce the Banach contraction principle together with some theorems which are related to this principle. And also I will try to present some application of this principle. So the outline of this presentation is given as follows. In the first, I will introduce, in introduction, and later I will present the contraction principle. And after, I will present some application of the Banach contraction principle. And later, I will present some generalization. And the last end, I will present some characterization of the complexness. A fixed point of a mapping T from a set into itself is an element X such that its image coincides with the element, that is T of X equal to X. The Banach fixed point theorem was not the first theorem connected with fixed points. Indeed, one of the first theorems were formulated by Henri Poincaré in 1886. In 1909, Brouwer proved that any continuous functions from a closed ball in Rn into itself has at least one fixed point. This proof was presented for the dimension n equal to 3. A year later, Adamar showed the generalization of this theorem for an arbitrary n. In 1912, Brouwer gave another proof for this generalization. The Brouwer theorem was a non-constructive result. It was only existential. It said about the existence of such a point, but did not explain how to obtain it. The proof of the Banach fixed point theorem was constructive. It gives the existence and uniqueness of fixed point and the convergence of the sequence of successive approximation to the solution of the problem. Banach's doctoral thesis, defended on June 24, 1920, was the very beginning of functional analysis. Banach's book, entitled Théorie des opérateurs linéaires, published in 1932, was the beginning of linear functional analysis. Fixed point theory is divided into three major areas. They are the topological fixed point theory, the metric fixed point theory, the discrete fixed point theory. I will give in the next an overview of these three major areas. Historically, the boundary lines between the three areas were defined by the discovery of three major theorems. The Brouwer fixed point theorem, which began in the topological fixed point theory, the Banach fixed point theorem, which belong to the topological fixed point theory, for the metric fixed point theory, and Tarski, the fixed point theorem of Tarski, is begun to the theory of discrete fixed point theory. Here are the references concerning this important fixed point theorems. The Brouwer fixed point theory has two versions. The first one states that every continuous mapping from a closed ball in Rn into itself has a fixed point. This version concerns the closed ball. As an example, any continuous map from a compact interval AB into itself has at least one fixed point. For the proof, we can consider the function f defined as f of x equal to t of x minus x, and we can show that f of a times f of b is less to 0. So since f is continuous, we can use the intermediate value theorem, which gives that there exists x stars such that f of x star is equal to 0. That means that x star is a fixed point of T. For the second version, in Rn, the compact convex sets are not only the balls. So the second version is more general than the first one and states that if K is a compact, convex, and non-empty subset of Rn, any continuous operator from T from K into K has at least one fixed point. The following counterexamples show the essential of each assumption in the Brouwer fixed point theorem. That means that I will give some counterexample that the continuity of the map is in essential condition. The same for the compact or the convex of the domain. So let the function f defined from the open interval 0a 1 into itself, defined by f of x is equal to x over 2. This map is continuous and maps the open interval 0, 1 into itself, but the domain is not compact. And we can see that this map has no fixed point. Another example, let K be R and take the map from K into K defined by T of X is equal to X plus 1. T is a translation map. We can see that T is continuous and K is convex, not empty, but not compact. And we can see that T has no fixed point. So, because the domain is not compact, so we cannot get a fixed point. Another example, let D be this set, and define the map on D by f of x0 equal to my x0. We can see that this map has no fixed point. Why? Because the domain is not convex. It is compact, but it is not convex. So this map has no fixed point. Another example, let the function f defined on the compact interval 0, 1 into itself, defined by f of x is equal to 1 if x belongs to 0, 1, open at 1, and it equal to 0 if x equal to 1. So this function has no fixed point. Why? Because it is not continuous at x equal to 1. So the continuity is an essential assumption, the same for the compactness or the convexity of the domain. Now, I will say some words about the discrete fixed point theory. Discrete point theory came from Alfred Tarski in 1955. Tarski fixed point theorem is a discrete fixed point result. Note that a discrete fixed point is a fixed point for functions defined on finite sets. Recall that a lattice is a partially ordered set in which every pair of elements A, B has a least upper bound called the join, noted A, V, B, which is the maximum between A and B, and a greatest lower bound called the meet, denoted by A meet B is equal to the minimum between A and B. Let me give some examples of lattice. Let X be a set and P of X the family of all subsets of X, ordered by the inclusion. Let A and B be element of P of X. Then A meet B is equal to the intersection between A and B, and A join B is the union between A and B. So we can see that this is a lattice and which is a Boolean lattice. Consider another example. Let n be the set of positive integers ordered by the divisibility. Let A be element of n, then A meet B is equal to the greatest common divisor between A and B, and A join B is the lowest common multiplicator between A and B. So we can see that this is a lattice which is unbounded. Now we state Tarski fixed point theorem, which states that if T is a monotone function on a non-empty complete set, then the set of fixed point of T is non-empty. The set of fixed point of T forms a non-empty complete lattice. T has least fixed point and a greatest fixed point. This theorem was presented by Tarski in 1955. Tarski result has many applications in computer science, economics, and other. For instance, discrete fixed point theorems have been used to prove the existence of Nash equilibrium in game theory. The Nash equilibrium of the game is defined as fixed point of a certain function. Now we give some words about metric fixed point theory. The concept of metric spaces was introduced in 1906 by the French mathematician Fréchet. Metric fixed point theory came from the Polish mathematician Stefan Banach. Banach fixed point theorem, introduced in 1922, is a useful tool in the study of metric spaces. It ensures the presence and uniqueness of fixed points of particular self-maps of metric spaces and gives a constructive approach to find set fixed points. So this is a reference about the introduction of concept of metric spaces by Frischit in 1906. Now we define what we mean by contraction map. Let the couple XD be a metric space, then T, which is a map from X into itself, is said to be a contraction on X if there exists a constant K between 0 and 1, such that the distance between Tx and Ty and Ty is less than K distance between X and Y. Let the couple XD be a complete metric space, and let T be a contraction on X. Then T has a fixed point, say U in X. Moreover, for any X0 belonging to X, we define the series or the Picard iteration as Xn plus 1 is equal to Xn for each n. Then the sequence Xn converges to the fixed point U, which is unique. Also, the rate of convergence is controlled as the following. So this equality gives the distance between the sequence Xn and the fixed point. This result was given by Stefan Banach in 1922. Unfortunately, there are some practical situation in which we have not a contraction, because the Lipschitz constant is not necessarily less than 1. So in this case, we can use a more general version of the Banach fixed point theorem, which is the following. Suppose the couple MD is a complex metric space, and suppose that T is a map defined from M into M, is a mapping such that the nth iteration of T, which is defined as the composition of T with itself n times, is a contraction mapping for some positive integers n greater or equal to 2. Then T has a fixed point. That means when T is not a contraction, we can get a fixed point for T. For this, we must show that there exists an iteration of T which is a contraction. So in this case, T has a unique fixed point. We give the following examples. Let T be the map defined on the interval 0, 2 into itself, defined by T of X is equal to 0 if X belongs to the interval 0, 1, and equal to 1 if X belongs to the interval 1, 2. We can see that this map is not continuous at 1, so it cannot be a contraction. But we can see that there exists an integer n such that the iteration of order n of T is a contraction. We can see that the iteration of order 2 of T is equal to 0, so it is a contraction. And in this case, we can say that T has a fixed point. We have the situation in which T is not a contraction, but there exists an iteration of T which is a contraction. So in this case, we can conclude that T has a unique fixed point. There are many applications of the Banach contraction principle. Let me introduce some of them. Initial and boundary variable problems for ordinary differential equations, partial differential equations, Newton's method for finding roots of equations, integral equation, optimization and game theory, probability and stochastic processes, computer science, and machine learning. I will give some details about these applications. Consider first initial variable problem. If we consider the following initial variable problem or the Cauchy problem, where f is a map from 0t times r into r, and y0 is an arbitrary element of r. So we can integrate this equation and obtain the following integral equation, this one. This is an integration equation of Volterra type. So we integrate the both sides of the equation and using the initial condition. So we can give the following result about this Cauchy problem. We assume that a function is continuous with respect to its both variables, and we assume that it is Lipschitz with respect to the second variable. Here we assume that k is positive. So if we assume h1 and h2, then the problem 1, 2 has a unique solution provided that kt is less to 1. In fact, this constant is the Lipschitz constant of the main operator that we win. So we consider this operator n from C into itself defined by this expression. We can see that the fixed point of n is a solution of the integral equation, which is solution of the Cauchy problem. And using h1 and h2, we can obtain that the norm of ny1 minus ny2 is less to kt norm of 1 minus 1 2. This norm is the norm of the uniform convergence in C, the norm supremum. So n will be a contraction provided that kt is less to 1. And in this case, we obtain that n has a fixed point. Unfortunately, in many practical situations, the Lipschitz constant of the main operator is not less than 1. Why? Because the Lipschitz constant is related to the parameters of the phenomena. So we cannot assume that this constant is less to 1 because it depends on the parameters of the phenomena. So there are another possibility to obtain the same result without assuming this condition, this one. Usually, this one is considered as a strong condition. So we shall show that there exists an iteration of n, which is a contraction. We know that without this condition, the operator n is not a contraction. So we shall try that there exists an iteration of n, which is a contraction. So we start with the second iteration. We can find that the second iteration is not contraction because the Lipschitz constant is not less to 1. And we continue until in integer n. So we obtain that the Lipschitz contraction of the operator of the nth of the iteration of n of order n is equal to kt power n over factorial n. But we can see that the limit of this fraction is equal to 0 when n goes to infinity. So we are sure that there exists in n, in integer n, such that this constant is less to 1. So we are sure that there exists an iteration of n, which is contraction. So in this case, we conclude that n has a fixed point, which is solution of the problem 1, 2. There are another possibility to obtain uniqueness result for the problem 1, but instead of using the classical uniform convergence norm, we use this type of norm, which was introduced by Bielecki. This type of norms are called the norm of Bielecki type. So we introduce this norm on the space C, the space of continuous function, and we can show that here we assume that tau is greater than 1, which is not a restriction. So we can show that the operator n is Lipschitzian, where the Lipschitz constant is equal to 1 over tau. So since tau is greater than 1, we obtain that n is a contraction. So it has a unique fixed point, which is solution of the problem 1, 2. Now we consider boundary variable problem, another class of ordinary differential equations. So we consider second order nonlinear differential equations subject to non-homogeneous Dirichlet boundary conditions, where f is continuous. We will assume that f is continuous with respect to the both variables. So we can integrate 2 times these equations, and using the boundary conditions, we obtain the following integral equation. That means that the given boundary variable problem is equivalent to this integral equation. This equivalence in the sense that the solution of the boundary variable problem is solution of this integral equations, and vice versa. This is an integral equation of Fredholm type, where the kernel is the green functions defined by this expression. G is called the green functions. So for more details about these functions, we can consult or this interesting books. So I will give some properties of the green functions. The green function is continuous over the square 0t times 0t. It verifies the homogeneous boundary conditions, and it is derivable on the square 0t times 0t, except the main diagonal. There are some sufficient conditions answering the existence of the green functions. So the functions exist provided that the following homogeneous problem has the trivial solutions. So if this problem has a trivial solution, then we are sure that the green function exists. There exists a method showing how to find the green functions. So for the who are interested in this question, then can consult one of these books. Voilà. There are many details about the green function. So we will assume that f is continuous with respect to its both variables, and it is Lipschitzian with respect to the second variable. Since g is continuous, so it is bounded. So if h1 and h2 are satisfied, then the problem 5, 6 has a unique solution, provided that Lg star t is less to 1. So we consider the following operator defined by this expression. We can notice that we have defined the operator n as the right-hand side of the above integral equations. So the fixed point of this operator will be solution of the integral equations, will be the solution of the boundary variable problem. So we can see that this operator is Lipschitz, where the constant of Lipschitz is given by this constant. So we assume that this constant is less to 1. Another application of the Banach contraction principle is about finding roots of equation. Let the equation f of x is equal to 0, where f is an arbitrary function that may be nonlinear. Set the following function g of x is equal to x minus lambda f of x, where lambda is a suitable constant such that g is a contraction. So we try to choose lambda such that g will be a contraction. So if there exists a constant k belonging to the interval 0, 1 such that the derivative of g is less to k, thus in this case we can see that g is a contraction. So a function is a contraction if its derivative is bounded by a constant belonging to the interval 0, 1. Let us take this example. We try to solve this equation x power 3 plus x minus 1 is equal to 0. Define the function g of x is equal to x minus lambda x power 3 plus x minus 1. So if we choose lambda equal to 0.5, then we compute the derivative of g, we obtain that g prime of x is equal to 1 minus 0.5, 3x power 2 plus 1. So if we assume that we work on the interval 0, 1, then we obtain that g prime of x is less to 1. So in this case, g is a contraction. So we will get solution of the considered equation. Now we try to give some generalization of the Banach contraction principle. Two questions arise. The first one, could we find contractive condition giving existence of unique fixed point in a complete metric without the map that continues? We see that for the Banach contraction principle, the continuity of the map is essential. So is it possible to find a fixed point for a map without being continuous? The second question is, could we have existence of fixed point without the space being complete? We have shown that the completeness of the space is essential to get a contraction map. So is it possible to get a fixed point without that the space is complete? So we'll see that we have a positive answer of these questions. Let us start with the response to the question A. In 1968, Cannon gave an affirmative answer. He considered this new contraction condition. The distance between t of x and t of y is less to this expression, with here k belongs to the interval 0, 1 over 2. This result was given by Cannon in 1968. Let me take this example. Take x equal to r, and let's take t, the map from x into x, defined by t of x is equal to 0 when x belongs to minus infinity 2, and equal to 1 over 2 if x is greater to 2. We can see that for this map, 0 is the unique fixed point. 0 is the unique fixed point. Even t is not continuous. We can see that t is not continuous at 2. So it is not contraction. So we have an example of a map which is not a contraction and has a fixed point. So the mapping T is a Cannon contraction with a constant equal to 1 over 5. We have the following remarks. Every contraction map with a contraction constant K is less to 1 over 2 is a Cannon map. If K is greater than 1 over 3, then the map is still a contraction. So we can use the Banach contraction principle, but it may not satisfy the Cannon condition when K is less to 1 over 2. So the Cannon map is more general than the contraction map. Cannon theorem states that each Cannon contraction mapping on a complete metric space has a unique fixed point. This result was given by Cannon in 1968. Now we give another version of Cannon theorem. This theorem states that let the couple XD be a complex metric space and the T is a map from X into X, be a Cannon contraction mapping. That is, it satisfies this condition. So where A and B are non-negative real numbers such that A and B belongs to the interval 0, 1 and their sum is equal to 1. In this case, T has fixed point, unique fixed point. Now we give an answer to the question B. There are incomplete metric spaces on which the Banach contraction mapping has a fixed point. Let X be the interval 0, 1, open at 1, be the interval on the wood with the usual distance. Define the map T from X into X, defined by T of X is equal to X over 2. We can see that T is a contraction mapping and has a fixed point, even the metric space is not complete. So we can get a fixed point for a map, which is not necessarily defined on a complete metric space. So this is an example of a map which is defined on a space which is not a complete metric space, but has a fixed point. So the following questions arise: how to generalize the Banach contraction, how to extend the Banach contraction principle to the large class of various spaces, does the converse of Banach contraction principle hold? Here, by the converse, we mean that does the complexness of the metric space implies that there exists, or that we can apply the Banach contraction principle. So let me start with another generalization of the Banach contraction principle. This result was given by Mir-Killer in 1969. It states that let XD be a complete metric space and X be a map from X into itself. We assume that there exists an epsilon greater than 0. We assume that for each epsilon, there exists delta, a positive number, such that the distance between X and Y is greater than epsilon and less than epsilon plus delta. And this implies that the distance between T of X and T of Y is less to epsilon. Then the theorem states that T has a unique fixed point. This proposition is more general or weaker than the Banach contraction. So this theorem was presented by Mir and Killer in 1969. Now we give some remarks about this class of maps. Each Mir-Killer mapping is continuous. Each Banach contraction mapping on a metric space, on a complete metric space, is a Mir-Killer mapping with delta here is given by epsilon times 1 over k minus 1, with k belongs to the interval 0, 1. In the Mir-Killer theorem, we should find delta, inappropriate delta. So in this case, for any epsilon, we can get the value of the delta. So each Banach contraction is a Mir-Killer mapping with delta is given by this expression. Now we give an example. Let n be a positive integer, and we consider X as the union between the interval 0, 1 and 3n and 3n plus 1 with the Euclidean distance d. Consider the map T from X into itself defined by this expression. So we can see that this map is a Mir-Killer contraction. T has a unique fixed point at 0. So we can show that 0 belongs to the interval and f of 0 is t of 0 is equal to 0. So 0 is the unique fixed point. But we cannot apply the Banach contraction principle. Why? Because from this equality, so we consider, for example, two elements, 3n plus 1 and 3n. So we compute their image and the distance between them over the distance between these two elements. So this quotient is the Lipschitz constant, but here it's equal to 1 plus 1 over n plus 2, which is greater to 1. So in this case, we cannot apply the Banach contraction principle. But this map is a mere Keeler contraction and has a fixed point. Now we introduce another generalization, Caristi theorem, which is introduced in 1976. Let XD be a complete metric space and the T be a map from X into itself. Then T has a fixed point in X, provided that there exists a lower semi-continuous function phi from X into 0 infinity, such that the distance between X and T of X is less to this one, this term. Here, phi is a lower semi-continuous function. So this result was presented by Caristi in 1976, which is a more class of mapping which contains the Banach contraction. Let me give some remarks. Recall that a function phi from X into R is said a lower semi-continuous at X if for any sequence Xn converging to X, then the limit f of phi of Xn is when n goes to infinity is greater or equal to phi of X, which is equivalent to that the set of X belonging to X, such that phi of X is less to A is closed in X for each A in R. Let me give an example of function which is lower semi-continuous. Let T be a function from R into R defined by this expression. Then we can see that this map is lower semi-continuous at X is equal to 0. There are a characterization of the lower semi-continuity. So we have the following result. T is lower semi-continuous at X equal to A if and only if the limit f of T of X when X goes to A is greater than T of A. So from practical point of view, this is useful to get the lower semi-continuous of a map. The fixed point for this class of maps is not necessarily unique. So we can say that each Banach contraction mapping on a metric space is a Caristi mapping with a function phi is given by this function. So each contraction map is a Caristi map with this function. We can say that this function phi is lower semi-continuous. Let me take this example. Consider X as the compact interval 0, 1 and D the usual metric. Choose T as the map from X into itself defined by T of X is equal to the square of X. Take, in this case, phi of X is equal to 1 minus X. So we get distance of X at, and the T of X is equal to this. So we can say that this map is Caristi type. So we can say that T has two fixed points. So for this class of maps, the fixed point is not unique, but it constitutes a large class of maps which contains the contraction map. For this example, we cannot apply the Banach contraction principle. Why? Because if we consider 2 points, for example, 0 and 1, and we consider the image between them and the distance, then we shall get that this distance is equal to the distance between 0 and 1. So here, the Lipschitz constant is equal to 1. So we cannot apply the Banach contraction principle. The function phi acts as a kind of potential guiding the motion. The condition says that the distance between a point and its image under t is controlled by the drop in the potential phi. Because phi cannot decrease indefinitely, it is bounded below, and is lower semi-continuous, then the process stabilizes at the fixed point. Now we give some connections between Caristi fixed point and other concept. Caristi's theorem is equivalent to Eklund's variational principle, which is a fundamental tool in optimization and variational analysis. Caristi theorem generalizes the Banach contraction principle. If T is a contraction, we can choose inappropriate function phi to make the Caristi condition holds. Caristi's theorem is equivalent to Takahashi's non-convex minimization theorem. Takahashi's non-convex minimization theorem is a result in nonlinear analysis that extend fixed point and minimization principle in the spirit of Banach's contraction principle to non-convex setting. So in the non-convex setting, we use the Takahashi non-convex minimization theorem. It is particularly useful for proving existence and uniqueness of minimizers without assuming convexity of the domain. Classical minimization results often require convexity of the domain of compactness assumptions. Takahashi's theorem removes convexity while still guaranteeing the existence and sometimes uniqueness of a minimizer by imposing a contractive type condition. For more details about the application of Takahashi's theorem and also Caristi theorem, we can see or consult this recent paper. Now we give another connection of Caristi theorem with the Eklund variational principle. This important theorem was introduced by Eklund in 1974, which states that let XD be a complete metric space and phi is a map from M into R plus, a map which is lower semi-continuous. Define the following relation, x is least to 1 if and only if the distance between x and y is equal to phi of x minus phi of y for each x, y belonging to M. Then this couple has a maximum element. This is an important result which was introduced by Eklund in 1974. Caristi and Eklund theorems have different setting. In fact, they are both equivalent. The proof of Caristi and Eklund theorems is based on discrete techniques like Zorn-Lemma and axiom of choice. So for this equivalence, we can see this paper. Now we recall what we mean by Zorn-Lemma and the axiom of choice, which are fundamental results in set theory. Let P, this couple, be a partially ordered set if every chain, which is every totally ordered subset of P, has an upper bound in P, then P contains at least one maximant element. The axiom of choice states that let A be a family of non-empted sets, then there exists a choice function f from I into the union of IA, such that f of I belongs to IA for every A. The axiom of choice is one of the fundamental principles of modern mathematics. It says you can choose an element from each set in a collection, even if there exists no explicit rule for making the choices. So for more details about this concept, we can consult this interesting books by Jesh and Almos. Now we introduce another class of maps which generalize the Banach contraction mapping. This theorem was introduced by Boyd and Wong in 1969. This theorem states that if XD be a complete metric space, and suppose that T is a map from X into itself, which satisfy that the distance between T of X and T of Y is less to phi of the distance between X and phi and Y, where phi is a map from 0 infinity into itself, which is upper semi-continuous from the right. That means, what we mean by upper semi-continuous from the right, that for any sequence Tn converging to T, then the limit sub of phi of Tn is less to phi of T. And we assume that phi satisfies that phi of T is less to T for any T. Then T has a unique fixed point. So this is a more general version of the Banach contraction principle. So for inappropriate function phi, we can get the Banach contraction. So sometimes we say that this map is a nonlinear contraction. Let me take this example. Let a T be a map from R into R, be defined by this expression. We can see that T is upper semi-continuous, X is equal to 0. So we have the following characterization of the upper semi-continuity. T is upper semi-continuous at X is equal to A, if and only if the limit sup of T of X is less to T of A. So this is a characterization of the upper semi-continuous, which is often it is usually because it is in practice it is more easy than the definition of the upper semi-continuity. Matowski considered the same contraction of Boyd-Wong with a non-decreasing function phi, which is defined from 0 infinity into itself, such that the limit of the iteration of phi of order n is equal to 0 for each t. And we assume that phi of t is less to t for each t, and phi of 0 is equal to 0. This result was given by Matowski in 1977. Let me give the following example. Let X be the interval 0, 1 union with the integer element from 2. We enjoy on X the complete metric. Distance of X to Y is given by this. So we can show that this is this distance. And we consider the map T defined from X into X by this expression. So we take the function phi defined by phi of T is equal to this expression. So in this case, we can show that the Boyd-Wong contraction holds. So T has a unique fixed point, which is equal to 0. But we cannot apply the Banach contraction principle. Why? Because when n goes to infinity, this quotient tends to 1. It doesn't tend to a constant which is least 1. It tends to 1. So we cannot apply the Banach contraction principle. So this is an example of a map which has a fixed point, and it is not a contraction. So this class of map can be considered as a generalization of the Banach contraction principle. Another generalization is given by Katerja. It is given in 1972. And it states that if XD is a complete metric space and T be a map from X into X, satisfying that the distance between T of X and T of Y is less to this expression, with chi belonging to the interval 0, 1 over 2. Then T has a unique fixed point. This result was introduced in 1972. And this class of maps contains the contraction map. We have another generalization which is given by Shirich in 1974. This result states that if XD is a complete metric space and T be a map from X into itself, be a quasi-contraction. That is, it satisfies the following inequality, with K is a constant between 0 and 1. Then T has a unique fixed point. This result was presented in 1974 by Sirich. This is a more general class of the Banach contraction. Now we give another extension in ordered metric space. We'll present a theorem which was given by Ran and Renix in 2004. This result states that let X be a partially ordered complete metric space, and T is a map from X into X. Be a monotone. That means if X is less to Y, then T of X is less to Y, T of Y. And we assume that there exists a constant K less to 1 such that the distance of Tx and T1 is less to K distance from X to Y. Then in this case, T has unique fixed point. This is a more general class of maps, which was introduced in 2004. Now we introduce the multivalued version of the Banach contraction principle. So this version was introduced by Nadler in 1969. A set-valued map T from X into the P of X, which is the family of subset of X, is said a contraction if there exists a constant K in the interval 0, 1, such that the distance between T of X and T of Y is less to K distance of X and Y. Here H is the Hausdorff distance between sets, because T of X is a set the same for T of X. So H is a distance between sets. So it is a distance introduced on the family of subset of X. And it is known as the Hausdorff metric, defined by this expression. A and B are bounded subset of X. If we take the following example, take X as R, A, the interval 0, 1, B, the interval 2, 4. Then we compute this one, this term, this one, and we compute this one. We are not necessarily equal. So we can find that this one is equal to 2. This distance, the supremum of this distance is equal to 3. So the maximum between them, which is equal to the Hausdorff distance between the sets A and B, is equal to 3. Now we state Nadler fixed point theorem. Let XD be a complete metric space and T be a map from X into the family of closed subset of X. We assume that T is a contraction with respect to the Hausdorff distance. Then T has a fixed point. That means that there exists X belonging to X such that X belongs to T of X. The particularity of this theorem that the fixed point is not unique. So the fixed point is not unique. So this is the multivalued version of the Banach contraction principle, which was introduced by Nadler in 1969. Now we introduce another theorem due to Gerald T, introduced in 1973.
Professor موافق.
Yes.
We can take a break if you wish. As I see, we still have many slides. If you wish, we
Yes.
can take a
Okay.
break of 5 minutes.
Okay. Yes. Okay.
So that you can drink some water if you wish. And we
Yes,
could
okay.
also have question
Yes.
from
Yes.
the audience if.
Yes.
So people in the audience, you can ask question. So are there any question?
I have a question.
Yes, yeah, go.
Yes. Yes.
When you have introduced the Bieliki norm for the affinity norm, for the sup norm,
Yes.
it is a weighted norm, which is equivalent to recover the contraction. Is that?
Yes. Often we
Uh,
call it as a weighted norm. Yes.
Yeah. Can we introduce that for the LP norm to apply this theorem without move to Schroeder class for the LP functions? Can we apply these techniques for the LP norms?
For the LP norm.
Yeah.
I'm not sure. I'm not sure. I'm not sure. No, I'm not sure.
Yeah, you
for
need to
example,
find the right way, probably.
Yes. Yes.
Okay. For example, if maybe as I have seen, maybe for example for the Friedholm operator, when we have a kernel, maybe we should get more assumption to the to the kernel.
Yes. 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 Of course. Often we assume that the kernel is continuous, even if not continuous, but the singularity are integrable. So in this case, I think then we can apply the Banach contraction principle.
Okay.
So often we assume that the kernel is continuous, even when it is not continuous, but it is integrable. Yes.
Integrable. Okay. Thank you.
Are there other questions?
Bonjour.
Yes.
Si vous permettez, j'ai une question. Je peux la poser en français, s'il vous plaît?
Oui, bien sûr.
D'accord. Donc, j'ai vu que vous avez parlé de l'action du choix
Oui.
et de son importance, mais j'ai pas vu un théorème de point fixe là où vous l'énoncez ou bien vous l'utilisez.
Non, c'est-à-dire que le théorème de Caristi, donc c'est-à-dire il a des applications donc dans le principe d'Eklund, mais seulement j'ai dit que, c'est-à-dire pour le principe d'Eklund, il est basé sur voilà, quelques concepts des ensembles, de la théorie des ensembles, en particulier donc l'axiome du choix et le lemme de Zorn. Voilà, c'est tout. C'est
Ok,
des outils
merci.
utilisés dans la démonstration du théorème, du principe d'Eklund.
Parce que l'axiome du choix, il permet de construire d'autres ensembles en choisissant
Oui,
un élément
oui,
de chaque ensemble, malgré
oui,
qu'on ne sait pas
oui,
comment le faire, mais on sait que on peut
oui.
construire cet ensemble.
Oui, c'est un résultat fondamental et il a pas mal d'applications, hein. Donc, en particulier, j'ai cité ici qu'il est utilisé dans le principe d'Eklund. Voilà.
D'accord. Dans la diapo 55, là, je pensais le théorème de Boyd-Wang.
Oui, oui, oui,
Là, enfin, il n'y a pas une contraction, mais en fait, on s'éloigne pas trop de la contraction, je pense.
alors c'est. Oui,
55, je pensais ma mémoire est bonne.
oui, alors je vais voir. Donc, voilà. Non, je pense. Oui, je reviens. Oui, pardon.
Je pense que c'est le théorème de Boyd-Wang.
Oui, oui, oui,
Ah,
ici.
vous utilisez,
Si
en
le-
fait, le théorème lui-même, il utilise une fonction phi de t qui est inférieure ou égale à t.
oui, si on prend phi de t égale à t sur 2, par exemple, kt avec k inférieur à 1. Donc, on va retrouver le principe de Banach. Ouais, excusez. Donc, alors, je pense que.
C'est
Voilà.
dans les 55 normalement. C'est dans l'énoncé du.
Alors, pardon. Donc, voilà. Voilà, c'est ça.
Voilà, moi, quand j'ai vu le sup ici, là, à un moment donné, il y a, je pense, phi de t inférieur à t, quelque chose comme ça, non? Oui, il est là. Revenez juste avant. Revenez juste
Oui,
avant.
voilà, c'est ça, c'est
Ah,
ça.
voilà.
Si on prend phi, la fonction phi définie par phi de t égale à kt, kt
Hmm.
avec k inférieur à 1. Donc ça va donner c'est k distance de x à y. Donc ça veut dire que c'est la contraction de Banach.
Oui, exactement. Mais en fait, c'était ingénieux. Ils ont pris, en fait, ils généralisent. Au lieu de
Oui,
dire la distance entre tx, ty inférieure à k fois la distance entre x et
oui,
y,
oui,
l'auteur du théorème, il prend une fonction phi, mais en
oui,
fait, les phi de t sont inférieurs à t. Ils se trouvent tous au-dessous de la première bisectrice. Donc,
oui,
en fait, ils ne s'éloignent pas trop de la contraction.
oui,
Je trouve que
oui,
c'est intéressant le théorème, c'est-à-dire il généralise le k qui est une constante à une fonction phi de t sans autant s'éloigner trop de
oui.
K.
Oui, ça c'est-à-dire même phi peut être non linéaire. C'est-à-dire même dans le second membre, on a la distance, mais sous une fonction une fonction, on peut avoir un carré ou un cube ou quelque chose comme ça. Euh,
D'accord.
Donc, phi, elle est quelconque, elle peut être non linéaire. Voilà.
Hmm. Ok, merci.
De rien.
As I
Merci.
see,
J'ai une autre question, si vous permettez, c'est juste pour vous demander des conseils. Quand on a des équations différentielles abstraites,
je me permets de vous interrompre. Peut-être on la laisse pour la fin si vous voulez, parce qu'il nous
d'accord.
reste encore 20 minutes, mais on peut en étendre un petit peu si vous voulez. Uh,
Ok,
Professor
merci.
Muwafaq, if you want drink, keep your question for
Oui,
the end. Professor
voilà.
Muwafaq, if you want to drink water, let's say, let's have 1 minute
OK.
and then continue.
D'accord, merci.
No, no. Yeah, we will go back to your question in the end.
Ça-
Okay. So Professor Muwafaq, we can resume whenever you wanna. I think we can continue if you wish.
Thank you.
Okay.
So we continue. The multivariate version of the Banach contraction principle was given by Nadler in 1969, which states that if X is a complete metric space and T be a map from the family of closed subset of X, which is a contraction, then T has fixed point. That means that there exists X belonging to the space X, such that X belongs to T of X. We mention here that the fixed point is not unique. Now continue with the, so I will, sorry.
Avec le sang.
Sorry. So now we continue with the more general theorems of the Banach contraction principle. The following is given by Gerardi in 1973, which states that if XD is a complete metric space and the T is a map from X into itself, satisfying this inequality, where phi or phi is a map from 0 infinity into itself, which is a function with phi of t is less to 1, phi is non-decreasing, and phi of t tends to 0, that when t tends to 0, then t has a unique fixed point, and for any x0 belongs to the space X, the sequence xn t of is equal to tn of x0 convergence to x star. Now we give the more general version of the Banach contraction principle for random operators. Let the triple omega fp be a complete probability space and xd be a separable complete metric space. T is a random operator from omega times x into x, meaning that for fixed x belonging to the space X, the map which omega to t of t omega x is measurable. That means that t is measurable with respect to omega. And t is a contraction if there exists a constant function depending on the parameter omega, which belongs to the interval 0, 1, such that we have this inequality. So in this case, the map T depends on the parameter omega, and it is measurable. So we can define what we mean by a contraction map. It is a map that satisfies this inequality, where here K depends on the parameter omega, and it belongs in the interval 0, 1. This theorem states that if T is a random contraction, then there exists a unique random fixed point, which is a measurable function, x, defined on omega into x, such that T of omega x is equal to x of omega for almost all omega in omega. So this is the random version of the Banach contraction principle, and what given in 1961 by Bachara and Keding. This theorem has many applications. Often when we are modeling the phenomena, we know that the parameters are not known exactly. So we cannot state the problem in determinist point of view. So we consider the problem from random point of view. So we can apply the fixed point theory. And in this case, we can apply this theorem, which is a generalization of the Banach contraction principle for random operators. Now we introduce more class of maps for fuzzy maps. So we introduce some definition. A fuzzy metric space is a generalization of metric space when distance described not by a non-negative real number, but a fuzzy set, indicating how close two points are, based on a degree of truth in 0, 1. The essential idea is that each element x belonging to the space x is assumed a membership grade, we noted by u of x, taking value in 0, 1, with u of x equal to 0, corresponding to non-membership. U of x is greater to 0 and less to 1. To partial, this means that we have a partial membership. And when u of x is equal to 1, then that means that we have a full membership. We give the following examples. The membership function of the fuzzy set of real numbers close to 1. We consider the class of real numbers close to 1. So we can define the membership functions of this fuzzy set, which is defined a of x is exponential minus beta x minus 1 power 2, where beta is positive real numbers. Now we consider the following example. Let the membership function of the fuzzy set of real numbers close to 0. So we consider the fuzzy set, which consists of real numbers which are close to 0. So this membership function is defined by b of x is equal to 1 over 1 plus x power 2. Using this function, we can determine the membership grade of each real number in this fuzzy set, which signifies the degree to which that number is close to 1. For instance, the number 3 is assumed a grade of 0.035. The number 1, a grade of 0.5, and the number 0, a grade of 1. Because if we replace x by 0, p of x is equal to 1. So we get the grade 1. That means that we have complete membership. Now we define what we mean by fuzzy contraction map. A fuzzy metric space is a triple x m star, where x is an empty set. M is a map from x times 0 infinity into 0, 1 is a function. Here star is a continuous T norm, usually minimum or product. satisfying the following condition for all x, y, z in X. S, T, and S are greater than 0. So this map satisfies these conditions. M of X, Y, T is equal to 0 if and only if X is equal to Y. M of X, Y, T is equal to M of Y, X, T. We have symmetry. M of X, Y, T is always greater than 0. M of X, Y, T star M of Y, Z, S is less to M of X, Z, T plus S. This map is non-decreasing with respect to the third variable. And we have the following condition, that the limit of M, X, Y, T when T goes to 0 is equal to 0. And the limit of M, X, Y, T when T tends to infinity is equal to 1. This concept of metric space, of fuzzy metric space, was introduced by these authors in 1974-5. Now we state the version of the Banach contraction principle for fuzzy operators. Let the triple X, M star be a complete fuzzy metric space, and let T be a map from X into itself, be a contraction mapping. That means there exists a constant C belonging to the interval 0, 1, such that M of Tx, Ty, T is greater than M of X, Y, C, T for each X, Y in X, and T greater than 0. Here C belongs to the interval 0, 1. Then in this case, T has a unique fixed point. And we can construct the fixed point as limit of a sequence. This sequence is given by this equality, which converges to the unique fixed point in the sense of physics on fuzzy metric. That means that the limit of M xn xt when n goes to infinity is equal to 1 for each t. So what we mean by that this sequence converges to the unique fixed point x. That means in the fuzzy sense, that means this equality is satisfied. So this fixed point was introduced in 1994 by George and Vera Mani. Fuzzy calculus developed for fuzzy members and fuzzy valued functions, used when uncertainty, vagueness, or imprecision cannot be modeled well by classical calculus. Below are some important applications grouped by field. In engineering, so fuzzy control systems, modeling system with uncertainty parameters, stability analysis of systems with fuzzy differential equations, robotic path planning under uncertainty environments. For example, fuzzy differential equations model temperature changes when sensor readings are imprecise. In economy, pricing models with uncertainty market conditions, investment decision making with vague risk assessment, modeling inflation, demand, and supply using fuzzy functions, forecasting with incomplete or subjective data. For example, fuzzy calculus helps model profit function when costs and revenues are not precisely known. In biological science, modeling biological systems with imprecise parameters, drug dosage control under uncertain patient responses, spread of diseases using fuzzy differential equations, medical image processing and diagnosis. For example, tumor growth models use fuzzy fractional calculus to handle variability biological responses. In artificial and machine learning, fuzzy neutral neural networks, learning systems with uncertainty or noisy data, hybrid fuzzy IL models, pattern recognizers, and decision-making systems. For example, fuzzy calculus supports learning algorithms where input features are vague. In physics, heat transfer and fluid flow with uncertain boundary conditions, climate modeling with imprecise environment data, quantum systems with fuzzy states, pollution dispersion modeling, for example, fuzzy partial differential equations model air pollution when emission data is uncertain. In social science, population dynamics with uncertain growth rates, decision-making models involving human judgment, risk assessment, and policy analysis. Now we introduce the version of the Banach contraction in probabilistic metric space. So first, we introduce what we mean by a probabilistic metric space, which is a triple XF tau, where X is a non-empty set, F is a map defined from X times X into delta, where delta is the set of distribution functions which are non-decreasing left continuous function f from R into 0, 1, with f of 0 is equal to 0, and limit of f of t when t tends to infinity is equal to 1. Tau is a triangle function, which is considered as a generalization form of the addition. F of x, y, t gives the probability that the distance between x and y is less than or equal to a value t. Now we state the theorem in the probability metric space. Let the triple XF tau be a complete probabilistic metric space. Let T be a map from X into itself, be a mapping such that there exists a distribution function phi satisfying that f of Tx T1 at T is greater than phi of T. Phi of T is greater than 0. Phi is strictly increasing, and the limit of phi of T when T goes to infinity is equal to 1. Then T has a unique fixed point, and the iteration xn plus 1 is equal to T of xn converges to x in the probabilistic sense. So this result was presented by Schweitzer and Sklar in 1960. Now we give yes.
Professor Muwafaq, yes? We still have only 5 minutes to conclude.
Okay. Yeah. Okay, so we can obtain another version of the Banach contraction principle in a bimetric space. That means here the distance is not a positive number, but a vector, c'est-à-dire which the value of the distance is a vector containing positive numbers. So we can define this space is a bimetric space. There are many examples. So this one. So we can define the main theorem in bimetric space, which generalizes the Banach contraction principle. Here in example. So we can also define in normed space, so that is the norm. Here the distance belongs to Rn plus. The same for the norm. We can define the norm. That means the norm is not in R plus, but in Rn plus. So we can introduce the matrix that converges to 0. So these are some examples. So we can introduce the theorem in generalized metric space, which is more general than the Banach contraction principle. So we can introduce some characterization. That means the complexness of the space is an essential assumption. So are there any possibility to characterize the complexness of the space? So this is possible, and this is given by many authors. So the space is complete if and only if characteristic mapping has a fixed point. A metric space is complete if only if Canaan metric mapping has a fixed point. So we can obtain many extension of the Banach contraction principle. As recognized of the Banach, in 2002, the government of Poland has provided 4 pieces of 4 coin. Here, coin of 200 zloty, as recognized of the contribution of the Banach. So the coin, this coin was made in gold and was devoted to the Banach fixed point theorem. These two are in here presented inequality characterizing bounded linear mappings on Banach spaces. So in my presentation, I was based on some references. This one, yes, there are books on the fixed point theory. There are some papers. So who are interested in the fixed point theory, there are many books related to this theory. So there are the book by Mebarki, Georgiev, Jubeli, and Zenir, recent book related to the fixed point theory. This is an interesting book, yes. Fixed point theorems and application by Pata. Okay. So this is my books. In fact, during my career, I'm interested in the qualitative and quantitative theory aspect of differential equations. I'm interested in the existence, uniqueness, oscillation, contrariability, and so on. So thanks to an international collaboration, we obtained many results and was published in many books from 2003, this one in 2006, about many topics. This one in 2012, this one in 2004, this one in 2015, this one in 2018, this one in 2023, this one in 2023, this one in 2023, this one recently. There are many topics considered in these books. So this recently in 2024, this one in 2024, and this one also about integral differential, which considered in the existence, uniqueness, stability, contrariability for various classes of integral differential equations. This one about also many classes of evolution equations. And the last one accepted in Springer, about fractional differential equations, in which we considered problems related to the Capito-tempered derivative. Thank you for your attention.
Let's thank Professor Muwafaq. Thank you very much for this presentation. So now time for additional question from the audience. Are there any question?
Yes, can I have a question?
Sure, yeah.
Yes.
Yeah. Thank you very much, Professor Ben Sharap, for this very nice and rich presentation. Maybe Badruddin has omitted to say that Professor Bashar has over 600 papers, which is really impressive, while still being very humble. And, this is very important to say. My question is about the applications of the fixed point theorem, because usually when considering, for instance, a PDE or an ordinary differential equation, usually we think about the contraction principle as a tool for theoretical study to prove the existence and uniqueness of the solution. But it is also, as you said, it gives also an algorithm to efficiently compute a solution. So my question is, what are the guidelines or the insights that you can give about how to choose the operator T to get good properties for theory, and also to have an efficient algorithm to find the solution? Thank you.
From numerical point of view, I have no idea. But there are toujours possibilités to use the Banach contraction principle. So from theoretical point of view, we can always consider the appropriate assumption to apply the Banach contraction principle. But from a numerical point of view, I have no idea. Of course, when we study problems, we are not obliged to use the Banach contraction principle. There are many tools that we can apply, but this principle has used widely in the literature, so it is an important tool in my point of view.
Other question? Ok, ça marche, oui.
D'accord. Donc, je tiens à remercier le professeur pour son exposé qui a été très riche. Il nous a fait quand même une synthèse d'un très bon nombre de théorèmes de points fixes. Moi, j'aimerais en fait lui demander conseil et non pas une question.
Oui.
D'accord. Donc, des fois, on prend des problèmes d'équations différentielles abstraites qui
Oui.
partent d'un espace de Banach vers un espace de Banach, où la fonction, le forcing term n'est pas nécessairement une fonction qui est continue. En général, on prend des générateurs de semi-groupes. Quels sont les théorèmes de points fixes que vous pouvez nous conseiller à part la contraction de Banach?
Ah, bien sûr. C'est-à-dire même pour les équations abstraites, parfois on peut avoir la représentation intégrale à l'aide de la théorie de semi-groupe. Même si l'opérateur A est à domaine dense, ou même lorsqu'il n'est pas à domaine dense, il y a d'autres semi-groupes qu'on peut utiliser. Mais lorsqu'il est à domaine dense, donc à l'aide du théorème de Yoshida, donc il génère un semi-groupe, et donc on peut avoir la représentation intégrale et par la suite utiliser soit le principe de contraction, soit d'autres théorèmes.
Type de contraction, c'est
certes.
trop.
Oui, c'est vrai.
Trop
Peut-être, en général, pour utiliser le principe de contraction de Banach, on est obligé de supposer que le second membre soit lipschitien. Mais parfois, certains seconds membres ne sont pas nécessairement lipschitiens. Mais il y a une possibilité d'utiliser d'autres théorèmes de points fixes, par exemple le théorème de Schauder. Mais aussi, chaque théorème a des avantages et des inconvénients. C'est-à-dire, il y a des situations où tel théorème peut ne pas satisfaire cette condition. Parce que pour le théorème de Schauder, on exige que l'opérateur est compact. Et parfois, surtout lorsqu'on passe aux dimensions infinies ou lorsqu'on fait appel à des opérateurs intégraux, un opérateur intégral, parfois le noyau, il est fortement singulier et ça peut poser donc des problèmes concernant la compacité de l'opérateur. C'est ça, parfois, la compacité de l'opérateur n'est pas satisfaite. Voilà. Donc, mais du point de vue théorique, on peut toujours s'arranger à imposer des conditions qui nous arrangent. Voilà. Mais ça n'empêche qu'il faut toujours essayer de minimiser, voilà, d'affaiblir les conditions, hein, voilà. Parce qu'il faut toujours penser au cas réel du point de vue appliqué dans des situations concrètes. Est-ce que ces conditions sont réalisables?
Mais c'est ça la difficulté, justement. Il faut...
Voilà, donc voilà, il faut voir, ça dépend. Donc ça dépend des problèmes et des conditions qui sont disponibles. Voilà.
Vous avez abordé aussi un espace, les espaces flous, je pense, phasés,
Oui,
là. C'est ce qu'on appelle les
oui,
espaces.
oui,
Est-ce que vous pouvez nous dire un peu, en résumé, sur
oui,
ces
bien
espaces?
sûr. Le calcul flow a plusieurs applications parce que le calcul flow c'est-à-dire les ensembles flow sont caractérisés par une fonction d'appartenance. C'est-à-dire que euh, euh, c'est-à-dire qu'on a un élément qui, lorsqu'il appartient à l'ensemble complètement, donc on dira, on lui associe le nombre 1. S'il n'appartient pas, on lui associe 0. Si on lui associe un nombre entre 0 et 1, ça veut dire que peut-être une partie appartient à l'ensemble. Ce n'est pas tout l'ensemble. Voilà. Donc, et ce calcul, il est très utilisé lorsque, par exemple, on veut modéliser un phénomène et les données dont il dispose ne sont pas connues exactement. Il y a toujours une incertitude. Donc, il vaut mieux utiliser le modèle du point de vue flou. Voilà, donc il y a pas mal d'applications concernant le calcul flou.
D'accord, merci.
Rien.
Donc, je ne sais pas ce que mon email apparaît chez vous, donc je ne me suis pas présentée. Je suis de l'université de Béjaïa.
مرحبا.
J'aurais dû le faire au départ, je ne sais pas. Donc, je suis Boulhia Fatiha, épouse talibé de l'université de Béjaïa. Je travaille un peu sur l'analyse fonctionnelle, quelques équations abstraites et on fait appel au théorème du point fixe.